Okay, our next speaker is Benjamin Cho from University of Texas at Austin, and he's going to talk about the compute topic. So it took us four talks to get to compute, a collaboration between CPU and NearData accelerators for machine learning training.
Hello, everyone. My name is Benjamin. I am a PhD student at UT Austin. Today, I'll be talking about collaboration between CPU and NearData accelerator for machine learning training. So for those of you not familiar with the concept of NearData acceleration, I'll give you a brief high-level explanation here. So for normal memory access, there are multiple memory units here, and among those, one will be selected from CPU and then will be accessed by CPU. But here, there is a point of bandwidth reduction. Especially this happens a lot in the high capacity DRAMs. And the concept of NearData memory acceleration is that by locating the processing elements between MUX and memory, we can scale the bandwidth along with the capacity. So in this way, also, we are accessing NearData so we can save energy for memory access. So the benefit of doing a NearData acceleration is high memory bandwidth and low access energy. So in CPU's perspective, it's an accelerator, but it's also still a main memory. And how are we going to use this unique position of NearData acceleration is the main question I want to answer here. So CPU already has a high capacity memory, so the NDAs are accelerators with high memory capacity. And also, since CPU and NDAs are sharing the same memory, they can collaboratively process the same data. So that is shown in the left figure here. And right figure shows just an example per rank NDA. So we can scale the bandwidth along with the number of ranks. But this architecture specifically uses a 3D approach, but it doesn't have to be in that way. There are some existing 2D approaches as well, but one thing to note here is that we have a memory controller on the memory side as well. So there will be two memory controllers, one at the host controller side and the other at the NDA side. And this solves the problem of command bandwidth issues for NDAs. So the question I had is, what will be an ideal scenario for CPU and NDA collaboration? There can be many different answers, but one answer I came up with is this. First, there should be two types of workloads with different requirements. First type will be latency-sensitive workloads, which will be a good fit for CPUs. And the other type will be throughput-oriented workloads, which will be a good fit for NDAs. And those CPUs and NDAs have to share large read-only data. So because it's large, data replication is expensive. And since it's read-only, we don't have to maintain coherence for sharing this data. So these are two requirements. And I was looking for is there any application that meets these conditions? And this SVRG is a machine learning optimization technique. To give you a brief explanation, there is a widely used SGD optimization, the stochastic gradient descent. But this SGD samples data and use this sample for learning weights. But since it's sampling, there are some variance introduced by the sampling approach. So what this SVRG does is periodically do a summarization step and then come up with a correction term. And this correction term will be used for the main training steps. And it helps reducing the variance. So here, the CPU is doing the main training. If you look at here, it's an inner loop. It samples a small lowercase a from the large input sets, and then it uses the a to update the next weights. And outside the inner loop, there is a summarization step, which requires accessing the entire data. So we for this summarization, we need a high memory bandwidth, which is a good fit for NDAs. So CPU is doing the main training, and periodically NDAs are providing the correction term to do better, to help CPU to get better accuracy. So this is a high-level idea. And since CPU and NDAs can concurrently access the same memory, we explore some algorithm change here. So in original algorithm, CPU and NDAs are sequentially executed. So CPU first do the inner loop, and then after a certain amount of iterations, it will execute the the summarization with NDAs, and that's one epoch, and it goes through the training loop. But what I am proposing here is a delayed updates. So instead of concurrently accessing these two, we are using a stale S and G term, which is from one epoch behind. So the per epoch time will be shorter, but we might need to execute more epochs because of this staleness. So this is the main trade-off in this study, this algorithm. And this is the collaboration results. Algorithm I'm using is logistic regression with L2 regularization. I'm using a CFR10 data set. And here I'm comparing the conversion speed. So the y-axis here represents how far you are from the optimum. And that means that the lower the better. And the host, I'm comparing the host only and accelerating the summarization with NDAs, but in the sequential manner. And the delayed updates is the concurrent access. So if you first look at the dotted line here, there are three of them with different epoch. So epoch n means first CPU samples n, the entire data sets, and do the updates, and then move on to the summarization. And as you can see here, because CPUs are slow and has a lower bandwidth, you cannot do it as frequent as you want. But with accelerator, actually, you get the best performance when the epoch is n/4, which means you only have to access 1/4 of data, entire data, to get the best performance. So I think this is a good way of using NDAs, because as a result of NDA execution, you can actually save the memory access from CPU. And with the delayed updates, you can further improve the performance. So to enable this, there are two main challenges. First is, so because we have a large data, we cannot replicate them and have a 2 copy of them and customize the data layout for CPU and NDAs. We need to have one common data layout for CPU and NDAs. And the second challenge is, so we have 2 memory controllers managing the state of the same memory. We need to track the global memory controller state somehow. So first, if you look at the example here, I am showing the XP operation. So basically, I'm accumulating the vector V to vector A. And with naive layout, so first you have to, I'll first explain why the data is laid out in this way. So in conventional CPU systems, they interleave, do the address interleaving to maximize the memory level parallelism. So if you look at here, the A0 is in channel 0, rank 0, and A1 is in channel 1, rank 1, and so on. So that's how, in this example, the address is interleaved. But in row Y, it has a different row address interleaving. So that's a problem because to enable an NDA, actually the data needs to be in local. So A0 and B needs to be in the same memory, but here you'll always have to read it from the remote memory, and that will dominate the performance. So the proposed layout here is we don't have to change anything from the memory controller side, but you only have to understand. You have to know how the memory controller is interleaving. And you have to group the rows that has the same interleaving pattern across ranks and channels. So in this example here, I'm assuming row X and row Z has the same, they're not exactly the same, but they are all local. So if you look at A0, B0, A1, B1, they are all in the same rank. So in this way, we can use the address interleaving for CPU as is, and yet we can also meet the rank locality for NDAs. And the second problem is, so there are two memory controllers. In this example, I'll show where there's a problem. So let's say the host memory controller is accessing memory 1. In this case, NDA1 memory controller can track the incoming host commands. But if you look at the NDA0 memory controller, it's actually internally accessing the memory. So this access is invisible to host memory controller if there's no backward signaling. So this becomes a problem because after alpha cycle, let's say the host memory controller now wants to access memory 0. But there's no way that host memory controller knows the bank and timing state of M0. So, since the NDA1 memory controller was keep tracking the host incoming host commands, it exactly knows the state of bank and timing. So it knows what command it has to issue and when it has to be issued. So the solution here is simple, replicating the FSM of NDAs. But this requires some standardization on the NDA operations. If you look at the left side, it's the host access, tracking the host access from the NDA. And the right side is actually where the is doing something new. So if you look at there, in the host side, there is a replicated FSM. And whenever there is an internal access, it already knows what kind of memory access there will be. And it will update the state of rank 1 accordingly. So to enable this concurrent access between CPU and NDAs, there must need some standardization on the address mapping interface for concurrently accessible data layout. And also for the low-cost memory controller state tracking, we need to standardize the NDA operations. And also, I have some other study going. Is on the concurrent access to different data. So previously, I was focusing on the collaboration, but there can be other applications accessing the memory, sharing the memory. In that case, there might be a contention between the accelerator and CPU, and we have to avoid that contention. And I use some sort of partitioning and some right throttling to solve the performance problems. So for the conclusion, there was an opportunity is collaboratively CPU and NDA can process the same data. And potential benefit was in our SVRG case study, we had a 2x faster conversion speed with a delayed update optimization. And the main challenge to to enable this collaborative execution is we need a common data layout for concurrent access, and we need to efficiently track the global memory controller state. And I solved it by with the interleaving pattern-aware memory allocation and the replicated FSMs. And there was other study about different concurrent access to different data. Yeah, that was it. Thank you for listening.